In this lesson, we're going to talk about an integration technique called integration by parts. And this is a useful technique when you can't use substitution and you don't have a direct formula to use. And this technique was derived from the product rule when you take derivatives. This technique can definitely be tricky sometimes and can sometimes be lengthy. So I highly suggest that when you use this technique that you take your time and you write down all of your steps to minimize the chance of you making an error. All right, let's walk through how the technique integration by parts was derived. So let's say we have a function h of x that's defined as the product of two other functions, f of x and g of x. Then when we take the derivative, we would use the product rule, and I would find the derivative of f of x times g of x plus the derivative of g of x times f of x. Now, if I use this equation right here, and I integrate both sides of this equation, I would get the integral of the derivative of h of x is equal to the integral of the derivative of f of x times g of x plus the integral of the derivative of g of x times f of x. Now, if I do a little bit of rearranging, and let's see, if I subtract this integral right here, the integral of the derivative of f of x times g of x, if I subtract that from both sides, then what I get is this is equal to the integral of the derivative of h of x minus the integral of the derivative of f of x times g of x. So we would get this equation here, and then this, if I take the integral of the derivative, I'm just left with h of x. And we defined h of x as f times g, so I'm listing that here. Now, because this is kind of messy, rather than use function notation, we're going to use u is f of x and v is g of x, and we're just going to substitute it so it cleans it up a little bit. So this is our final result. All right, we're going to start off with an easy example. Use integration by parts with u is equal to x and dv equal to sine x dx to evaluate this integral here, the integral of x times sine x dx. So we're saying x is u and sine x dx is our dv. So the first thing we need to do when we write this down, and this isn't always going to be given to us. This is given to us because this is our first example and we're trying to make it easy on you. So eventually you're going to have to identify these values. So we're going to start off that u is x, which means when I take the derivative of u, I get 1 times dx, which is dx. Now dv we identified as sine x dx. So to work backwards to find v, because we need to find u, du, dv, and v in order to do this integration by parts. So to identify what v is, we need to work backwards since we were given dv, and we need to find the integral of sine x dx. Now, when I find the integral of sine x dx, that gives me minus cosine x plus our constant. Now, I put this in here, this constant in here on purpose this first time, but to be honest with you, you don't really need it in here. What's going to end up happening when you use integration by parts, this constant is going to actually end up canceling out, and it's going to be unnecessary to put this in. So you can put it in, but in the future, if you want to omit this to save yourself a little bit of work, when it comes to integration by parts, you can do that because this is going to be unnecessary and things drop out. Okay, so here's our formula for integration by parts. We take the integral of u dv to get u times v minus the integral of v du. Since we identified all of these values up here, we're just going to plug this into our formula. So u dv is x times sine x dx. This is my u, this is my dv. Then I take my u times my v. My u is x. My v we got is minus cosine x plus our constant. Then we're going to minus the integral of v du. That's this part right here. So I'm going to subtract the integral of v du. So here we go. So this is our v, this is our du, or dx. Now, when I clean this up and I expand this, I get x times minus cosine x. That gives me minus x cosine x. And when I take x times our constant, we get our constant times x minus this integral. So I'm minusing whatever I get for that integral. I'm going to get, for the minus cosine x, when I integrate that, I'm going to get minus sine x. When I integrate this c for my constant, I get my constant times x. And then I have another plus c that I'm integrating with this integral. So I labeled that as c star, so that way you can tell the difference between the two c's. All right, now I'm going to clean this up some more. I'm going to distribute this negative here. This I'm just carrying down. I'm going to distribute this minus here. So that's going to give me a plus sine x minus the constant times x plus our c star. So as you can see, this constant is going to end up disappearing and it doesn't even matter. So that's why I'm saying this doesn't particularly matter if you want to leave it out. All right, so we've got minus x cosine x plus sine x plus this constant that's left from when we integrated this one here. Now, you can always work backwards and check it. And I highly suggest you do this the first few times because it helps you understand what's going on. If I want to make sure that this worked, I would take the derivative of this and make sure I get x sine x, just working backwards. So when I take the derivative of this, for this one here, I have to use the product rule. So if I take the derivative of negative x, that's negative 1 times cosine x, that's this. Then I'm going to multiply by negative x times the derivative of cosine x, which gives me minus x times minus sine x. And then the derivative of this is cosine x. And then the derivative of this constant is 0. So now if I clean this up, I get minus cosine x plus cosine x. That disappears, and I'm left with this. And these two negatives make it a positive x sine x, which you can see it worked. So I highly suggest the first few times you do this, you actually find the derivative, work backwards, and verify it. Our next example of integration by parts, we're going to evaluate the natural log of x over x to the third dx. Now, in this example, the author of the question did not indicate what we should let u and dv be equal to. So we're going to have to take an educated guess. Now, the thing about this is sometimes you take a guess what u and dv should be equal to, and it doesn't work out. And if that's the case, then you just start over and try something else. So this can be a little bit lengthy because sometimes you have to try a couple different things until you find something that works. However, I do promise that after you do this enough times, you start to get a little bit more intuitive about what you should let u and dv equal to. So I'm going to let u be equal to the natural log of x. And I'm going to let dv be equal to x to the negative 3. So I just rewrote this as x to the negative 3 and brought it up in the numerator. So to find du, I'm going to take the derivative of u, which is 1x dx. To find dv, I got to work backwards and find the integral of x to the negative 3 dx. And that will give me 1 over negative 2x squared. So now I have this information. I have my u and my v and my du and my dv, and I can use integration by parts. Okay, so we have our integral, and we're going to start off by doing u times v. Here's my u, the natural log of x. Here is my v, 1 over negative 2x squared. And then I'm going to minus the integral of v du. Okay, so here's my v. Here is my du. And now I just have to clean it up and work it out. When I combine this and clean this up, I get negative natural log of x over 2x squared plus this negative and this negative, I changed it to a plus so it's less messy. And I made that 1 over 2x to the third. Now this x to the third is coming from the fact that I have this x squared and I'm multiplying it by this x in the denominator. Okay, so now I'm going to carry this down. When I integrate this, I get 1/2 times 1 over negative 2x squared. And then I have to add in my constant and then clean it up further, and this will be my final answer. In this example, we have an integral in which we need to perform integration by parts twice. Kind of like sometimes we have to use the chain rule twice. So I labeled it here 1 and 2 for each time we use integration by parts. So the first time we use it, I'm going to let u be equal to x squared. So this is my u. And then I'm going to let my dv be equal to this part here. And so I find my du and my v that corresponds to the u and the dv. So du, when I take the derivative of u, that's 2 times x dx. When I find v, I have to work backwards from dv. So I have to integrate e to the 3x dx, and I get 1/3 e 3x. So now we have all of these 4 pieces that we need in order to perform integration by parts. So here's the integral that we're trying to evaluate. Here's my u times my v. Here's u, which is x squared, times my v, which is 1/3 e to the 3x. And I'm going to subtract my integral of v du. Here's my v, and here's my du, the 2x dx. Now, I clean this up a little bit. I get 1/3 x squared e to the 3x minus this 2 and this 3. I'm going to bring it out front as a constant, 2/3. And then I'm left with x e to the 3x. So this integral right here, we have it so that it looks very similar to what we started with. It's just that now we have it as x instead of x squared. So we broke that x squared down into an x. Okay, so we're going to perform integration by parts a second time. So keeping in mind that we still have this out in front and we just need to rewrite this again using integration by parts. So I'm going to let u be x and dv be the e to the 3x dx. So I'm going to find all of my 4 parts needed for the second integration by parts. So when I take the derivative of u, I get dx. And then when I find v using dv and I work backwards and integrate, I get 1/3 e to the 3x. So this part here, I'm going to carry down. That's this part right here. And then I'm going to minus 2/3. And then inside here will be my second integration by parts from this integral right here. So I'm going to take my u times my v, that's this part right here, for my second integration by parts. Here's my v, Here's my u, and when I multiply them together, I get 1/3 x e to the 3x minus the integral of v du. So here's my v, and here's my du. Okay, now we have everything set up, and now from here, we just have to clean it up and finish the integration. So this was this piece from up here, that from the first time. I'm going to carry it down. I am going to distribute this -2/3 here and here. So when I take -2/3 times 1/3 here, I get this 2/9. And then, of course, I still have the x e to the 3x right here. Then this negative and this negative, when I multiply, I get a positive. So I have the 2/3 in front of my integral here, and I'm bringing down the 1/3 e to the 3x dx. Now I could also bring this 1/3 out in front and make that 2/9, and that's totally fine. So in this last step, this carries down, this carries down, and when I integrate this, I get 2/27 e to the 3x plus my constant. Okay, here's another example of applying integration by parts. However, in this example, we are going to rearrange the function a little bit before we start. So instead of writing this as t to the third times e to the t squared, I'm going to separate a t from this t cubed and put it in with this function here. So I'm going to rewrite this as t squared times t e to the t squared. So this is my u, and this will be my dv. So I have u is equal to t squared. So when I take the derivative, I've got du is equal to 2t dt. Now this here is my dv. So this is what I have here, t e to the t squared. And when I integrate, I'm going to get 1/2 e to the t squared for my v. Now, I'm going to take this and rewrite it for integration by parts. So here's my u times my v minus the integral of my v. Here's my v, and then here's my du. Now I can clean this up a little bit. I'm going to rewrite this so that I have t squared in the numerator times e to the t squared all over 2. This 1/2 and this 2, when I multiply, I get 1/2 times 2 is 1, so I don't have to write that in anymore. And then I'm going to bring this t out in front just because I prefer it that way. So I have t e to the t squared dt. Now from here, I still need to integrate this. So I'm going to use u substitution here. I'm going to let u be t squared. So when I take the derivative of u, I get 2t dt. And since I need to replace the t and the dt, I'm going to solve for t dt and get that I'm going to replace it with 1/2 du. So this becomes e to the u, and this t and this dt become 1/2 du. So I rewrote that down here. So this comes down here. This I just recopied over. And this is where I did my substitution. Now when I finish, this is going to come down here and carry it down again. And then when I integrate this, I'm going to get 1/2 e to the u plus my constant. And then when I go back and resubstitute in terms of t, I get u is t squared. So I go back and substitute for u. So this will be my final answer. In this example, we have another integral that we're going to have to use integration by parts more than once. So here's my first integration by parts, and then this is where I start it the second time. Now, the first time we use this, I'm going to let u be sine ln x. So dv is going to be dx in this case. Now, when I take the derivative of u, I get cosine ln x, and then I have to take the derivative of that inner function because of the chain rule. And so I'm going to multiply by 1 over x, and then, of course, I have the dx here. Now, when I look for my v, given that I have 1 dv is equal to 1 dx, I'm going to work backwards by integrating, and I'm going to get the v is equal to x. So here's the integral that we're trying to evaluate. Using integration by parts, here's my u times my v, and I'm going to subtract the integral of v, and then here's my du. Now, I can clean this up by pulling this x in front. That's just my preference. You don't have to do that, though. And then I can take this x times the 1 over x, and that's just going to give me 1, and then times cosine ln x. So that's here. So the 1 over x and the x divide out, and you just get 1. So this is what we have so far. Now, I have to use integration by parts again to evaluate this integral. So for this integral here, I'm going to do the same thing as we did last time, but I'm going to let u be cosine ln x, which means du is going to be minus sine ln x, and then using the chain rule, I have to multiply by the derivative of what's inside. So that would be times 1 over x and then dx. dv is going to be 1 dx. So when I integrate to work backwards to find v, I'm going to get the v is x. So I'm going to carry this down. This is what we had before. This is where we left off. So I had x sine ln x minus the integral of cosine ln x. Now this comes down, and I get x sine ln x minus, and then I'm going to integrate this. That's going to go inside these brackets, and that's where we're going to do the integration by parts the second time. So here's my u, here's my v. My u is x, my v is cosine ln x, minus the integral of v du. So here's my v, here's my du. Okay, I carry this down again. This comes down. I'm going to distribute this minus sign and try to clean this up a little bit. So I have minus x cosine ln x when I distribute this minus. Now on this minus here, this comes from 3 minuses. I have this minus, and then a minus inside the integration. So the 3 minuses, that leaves me with a minus here. And then this x times 1 over x, that becomes 1. And I'm left with just sine ln x dx. Okay, now notice that we have the same thing we started with the first time around. If this happens, what you can do, since these do not have integrals in them, this is completed, I can add this integral to both sides, so I have 2 of them over here, and then I can solve for this integral by dividing both sides by 2. So if we used integration by parts again to do this, we would just end up in a horrible cycle that never ended because we would just start over from the beginning. So if we add this integral to both sides, we have 2 of them, and then we can find that integral by dividing both sides by 2. Now, if you have to perform integration by parts with a definite integral, you're just going to evaluate this just like you normally would on the interval from a to b. So you have to do that with the part that doesn't have the integral in front of it and with the part that does have the integral in front of it. All right, so here's an example of integration by parts with a definite integral. We're going to find the area of a region. Find the area of a region bounded above by the graph of inverse tangent and below by the x-axis on the interval from 0 to 1. So we're looking for this area, this blue shaded area right here. So we're going to integrate to find this area under the curve. We're going to integrate from 0 to 1 the inverse tangent. We're going to use integration by parts by letting this be u and this be dv. So we're going to let u be inverse tangent and dv be 1 dx. So here's my u, here's my dv. Now when I take the derivative of u, I get 1 over x squared plus 1 dx. If it's been a while since you've taken the derivative of inverse trig functions, you can use the reference sheet that I gave you that has the list of all the rules for the derivatives and integrals on it to look that up. Now we have dv is 1 dx, so working backwards, we integrate 1 dx to find v, and we get that that's x. So now we have from 0 to 1, inverse tangent is, here is my u times my v, but because this is over a specific interval, we want to make sure that we evaluate that from 0 to 1. And then we're going to minus the integral v and then du. So here's my v, here's my du. So when I integrate x times inverse tangent x from 0 to 1, I'm going to get pi over 4. Now I still have to evaluate this integral here. This integral here, I'm going to use u substitution. I'm going to let u be x squared plus 1, and then du is going to be 2x dx. And since now I have 1 over u, this will be my u, I still have to replace the x dx. So when I solve for x dx, I get 1/2 du. Okay, so now I have, if I scroll down here, I have pi over 4 that I brought down. Then I have 1/2 du over u. Now, because this is a definite integral and we just did a u substitution, I have to make sure that I remember to change my limits as well. So if x is 0, so I put 0 in here, I find that u is 1, so I replace this with 1. Now, the upper limit, which was 1 for x, if x is 1, then u is going to be 2. So now we're going to do this on the interval from 1 to 2. Again, keep bringing down that pi over 4. When I integrate this, I get 1/2 natural log of u, and I have to evaluate this piece from 1 to 2. So when I plug in 2, I get 1/2 ln 2 minus 1/2 ln 1. Whoops, I forgot my 1/2 there, but it doesn't matter because it's going to be 0 anyways, but I should have a 1/2 in here. When I do minus 1/2 natural log of 1, this is 0, and then 0 times 1/2 should be 0. So this just disappears. And so I'm left with pi over 4 minus 1/2 natural log of 2. All right, in this last example, we're going to do another integration by parts example, but with definite integral. And we're going to do it when we're finding a volume of revolution. So it says find the volume of the solid obtained by revolving the region bounded by the graph of e to the negative x with the x-axis, the y-axis, and the line x equals 1. And we're going to revolve it about the y-axis, so we're spinning it this way. So in my opinion, I think the best method for this would be to use the shell method. So we are going to take 2 pi r being the radius of the shell. So the radius of the shell coming out this way is going to be x. So we have 2 pi the radius, which is x, times the height, which is going to be the value of the function. So that's going to be e to the negative x. And we're going to do that on the integral from 0 to 1. using integration by parts, we're going to let u be x. So this is going to be the u. This is going to be the dv. So u is x, which means du is going to be dx. This will be the dv. So when I integrate and work backwards to find my value of v, I'm going to get that my value of v is minus e to the negative x. So here's my integral, and I'm going to set it up using integration by parts. I have this 2 pi in front, and I'm going to put everything in brackets. So using integration by parts, I'm going to take u times my v. So that's x times a negative e to the negative x. And I need to evaluate that from 0 to 1. So there's my u times my v, minus my integral from 0 to 1 of my v and then my du. All right, now I'm going to, when I evaluate this piece here from 0 to 1, if I plug in the 0, this whole thing disappears because of this x right here. When I plug in the 1, I get 2 pi times negative e to the negative 1. So that's this right here when you simplify it. The minus 2 pi, and then e to the negative 1, I put the e downstairs instead of having a negative exponent. Now I have 2 pi times this. Now this negative and this negative, I made it a positive here. The 2 pi is still in front, and then I have 0 to 1 e to the negative x dx. I carried this over right here. I carried this 2 pi over, and then the integral of this, when I integrate e to the negative x, I'm going to get negative e to the negative x, and I've got to evaluate that from 0 to 1. So I'm carrying everything else down. When I evaluate this from 0 to 1, I have this 2 pi in front. This is what I get when I evaluate it from 0 to 1. And then when I clean all of this up and combine like terms, I get minus 4 pi over e plus 2 pi.